Now I continue with the homework, the exercises that are in the book. And as you know, the solutions to the exercises in the book are in the back of the book, not for assignments, but for exercises, yes. So I will not discuss all of them, just a few remarks I want to add to them. And I start with the exercise 2.5.3 that you see here now. Well, the solution is written below. But anyway, this is typical of empirical science. I told it before that you do some observation, that is in part A, and you have a theory. So then you can use the observation and your theory to calibrate some things, such as to calculate utility of 50, for instance. And then you can use the observation and the theory to make predictions. That happens in part B. So this is the typical pattern of empirical sciences. Now I go on to another exercise I want to say something about. That is exercise 2.6.4. Yeah, that exercise is about the uniqueness of utility and expected utility. So assume that expected utility holds with a particular utility function, capital U. Then we ask the question, would there be other utility functions such that expected utility with those other utility functions would also work? And the answer is yes. For instance, ignore tau for a moment. Assume first that we multiply that utility function capital U that we have by a positive factor sigma. What happens? Well, then all the expected utility of all the prospects get multiplied by that positive factor sigma. That means that any ordering between them remains the same. So that means that the preference relation represented by expected utility then is the same as it was, so the right one. So that means that such a utility function, just as well, if you use that to do expected utility, you also have a good expected utility model. So indeed, you can multiply your utility function by any positive factor that you like, and still it's a good utility function. Something else that we can do is add a real number tau. Tau can be anything positive, negative. Then what happens if you replace your function capital U by capital U plus tau? Well, what happens then is that all the expected utilities of the prospects are increased by that same number tau. That means, well, for that, it may be good to realize that probability is always add to 1. So in every summation of expected utility, the total weight of 1 is assigned to tau. So it is true, indeed, that all the expected utility of all the prospects are increased by that constant tau. Well, if that happens, that means that the ordering between them doesn't change, so the preference relation represented by them doesn't change. So it is still representing the same preference relation that we had, the good one. So it is also a good utility function to be used in expected utility. So indeed, if you have a utility function, capital U, whatever it is, you can multiply by any positive number, you can add any real number that you want, and still the expected utility criterion with that new function works just as well as the previous one. So those are liberties that you have. A question can be raised that is not asked in the exercise, but I do want to discuss briefly with you. That is, would there be other utility functions that also work, or is this the only liberty you have? And the answer is, this is the only liberty that you have. There are no other utility functions that would work, except the ones that we described a moment ago. I will not fully prove it to you, but I'll give you the gist of the reasoning, and I'll do that using a figure that we saw before, figure 2.5.3 down here, the standard Gabel figure. Now, imagine we have expected utility. Now, I can choose any number to be the utility of capital M, and I can choose any other number to be the utility of small m, as long as the second is smaller than the first. I can always, whatever utility function I start from, I can choose sigma and tau, such that I get those desired numbers as the utility values of those capital M and small m outcomes. That liberty we have, we already saw it. I claim there is no other liberty, because once you have a utility function with capital M and small m having the utility as they do, then for all the other outcomes, utility is uniquely determined. For all other outcomes between capital M and small m, at least at the first, because you have seen for them that here is the standard Gabel for measuring utility. And you have then that the utility of alpha is p times utility of capital M plus 1 minus p times utility of small m, so that's uniquely determined. And then it is the function that we already saw, that linear transformation. Similar reasoning holds for outcomes that are not between capital M and small m, that are bigger than capital M better, or that are worse than small m. Then we have to use other indifferences, or we have to take bigger capital M and small m. But it can be shown, and I'm gonna skip the exact explanation of it. It can be shown that no matter how big your outcome space is, and if utility is unbounded, it doesn't matter. Always, you don't have more liberties than the two that I said. After choosing two values and then sigma and tau determined by that, after that, all the utility of all the outcomes are uniquely determined. So indeed, there is no more liberty than what we saw so far. By the way, this exercise also justifies something that I did a few times in the course up to now. So I would often just choose where utility was 1 and choose where utility was 0. And I always told you, take my word for it that it can be done. Just give me this one. Now, this exercise that we just discussed justifies doing it. Now you've seen, indeed, we have the sigma and tau free to choose. We can always, for two utility values, capital M and a small m, we can always choose the utility levels as we like, for instance, 1 and 0, as long as for capital M it is bigger than for small m. So that point in my course is now justified, that I made a few times. I want to go on to the next exercise that I want to say something about. That is 3.3.1. That's again the bike insurance example. We already discussed it in the first meeting, which is to find the expected value. Here we are assuming expected utility with objective probabilities. So now we assume that objective probabilities of the bike being stolen or the damage or whatever, that those are available. We do assume here that utility is linear, moderate amounts of money. Rule of thumb is whenever it is less than 2 months' salary, then take utility linear. So that is assumed here. Then, does expected utility now with objective probability, does it recommend insurance? Well, if there are very well-established objective probabilities available, the insurance company will have them, and they will have taken care that the premium is such that the expected value is positive for them. Because otherwise they will go broke with all their many clients and law of large numbers. They get the expected value on average. So the expected value is positive for them. Then as the minus of that is negative for you. So still negative expected value will still not do. So the reasoning, this is quite the same reasoning that we saw before. If you have objective probabilities available, it doesn't change anything in the reasoning. So still don't insure your bike or don't make any other small insurances. I know there is some more to think about, and my students bring it up and write so. For instance, it can be said that these probabilities, they are the probabilities of the average client of the insurance company. And it can be the case that you are different, that maybe you have much more risk than the average person. So that in your case, the risk is so big that the insurance would be worthwhile. Well, the point is that this is not likely to happen. Because, maybe I should say it is already happening more than you want to. Maybe I'll put it like that. Because usually only those people insure the bike who have a big risk of the bike getting stolen. And so therefore, if you have a bigger risk than the average person, you don't have a bigger risk than the average insured person. The insurance company is already reckoning with that. It's already in your premium. So your premium is already a premium for people who have high risk. And only if your risk is very exceptionally high, then maybe it is worthwhile. But there are other drawbacks to insurance. So they have the transaction cost, they must make profits. And there's one other point that you can consider as moral hazard. Sometimes people say, if I am insured, then I need not worry, I need not be careful with my bike anymore. But the problem is that, again, the insurance company knows it. All the insurance clients are like that. So it's already in your premium. So you're paying already a too high a premium, even if you're careless with your bike. So that's only, and if you're careful with the bike, it's only the more reason not to insure. The same way, if you're not very exceptionally high risky, then only the more reason not to insure. So these properties of adverse selection and moral hazard are only extra arguments against insurance. Only if you have very exceptionally high risk, it becomes worthwhile. Okay, here I finish discussing this homework. There was some more. You had to fill out figures 4.1.4 until 4.1.5, but those I'm going to discuss separately in the next recording.